Welcome to ratios versus two related amounts. So thus far, we've divided our data section into two types, single units and ratio units. Now sometimes these are the only distinctions that we need to solve a problem. But in more complex problems that ask for multiple answers, in other words, multi-part problems, then you need to select the correct data to use in each part of the problem. And to help you with this, you will need to be able to distinguish between ratios and two related amounts. And this now gives us three types of data: single units, ratios, and two related single unit amounts. So remember that single unit data measures an amount of an object or a process. And single unit data may measure a fundamental or a derived quantity. It may have a prefix, it may be a multiple of a base unit, like hour is 3,600 seconds, or it may be a power of a base unit, like cubic meters. But it must be defined using only one base unit in the numerator and no unit in the denominator. A ratio does not represent an amount or two amounts of some physical quantity. Instead, the ratio represents the relationship between two different quantities. That is, a ratio must have two measurements to it. And so we can write a ratio in the data section as either an equality or as a fraction or ratio or conversion. And these terms, fraction, ratio, conversion, those are all equivalent. So some examples of ratios are the metric prefix definitions, like 1 kilometer is 1,000 meters. Or conversions relating two units of the same dimension, like 1 minute equals 60 seconds, or some derived quantities are defined as ratios like concentration, speed, density, molar mass. And the coefficients in a balanced chemical equation show the particle-to-particle ratios in which that reaction occurs. Now, our last type of data, which is two related amounts, is two amounts that are related because they both measure the same object or the same process. And if this relationship involves two different dimensions or two different substances or entities, then those two related amounts are called an equivalency. So two related amounts supply us with three items for our data. They give us two single unit amounts, but they also give us a ratio between those two amounts. For example, suppose a problem tells us the car traveled 84 miles in 2.0 hours. We know two single amounts. We know the car traveled a distance of 84 miles, but we also know the time required for the car to travel was 2.0 hours. But that's not all we know. We also know the ratio. We know the average speed of the car. Remember that speed is distance over time, so speed is a ratio. So we know that the average speed of the car is 42 miles per hour. So we have this ratio of 84 miles to 2 hours, or 42 miles per hour. That's a ratio between miles and hours. And we can write that this way as 42 miles per hour. We can write that as 84 miles divided by 2 hours, or we can write that as 84 miles equals 2 hours. So suppose we've got two problems, problem A and problem B. Here we're going to look at problem A. Problem A reads, the car traveled 42 miles in 1 hour. And thus far, we've written in our data, 42 miles equals 1 hour. But the reason that these two amounts can be written as an equality is because they measure the same object or process, the trip that the car traveled in two different dimensions, distance and time. So we can really say the trip is equal to 42 miles. But the trip is also equal to 1 hour. And thus, we can say the trip is equal to 42 miles, which is equal to 1 hour, and that means that 42 miles is equal to 1 hour. So the wording of problem A provides us with two single unit amounts and a ratio between those two amounts, which we've written here as an equality, that we can then use as a conversion factor. So suppose the problem B reads, the car traveled 42 miles per hour. We can write in our data 42 miles equals 1 hour, but this equality is different than the equality that we had from problem A. In problem A, we know the total distance the car traveled, 42 miles, and the total time the car traveled, 1 hour, and we can find the average speed over the trip, 42 miles per hour. But in problem B, we don't know how long the trip was, either measured in distance or in time. And thus all we know is that average speed over the trip. All we know is that ratio between miles and hours. So we just have that equality, but we don't have any single unit amounts. So we need a way of distinguishing between a case where we're given just the ratio, as in problem B, and a case where we're given the ratio and 2 single unit amounts, as in problem A. So when you're given just the ratio, label the equality with an R. And when you're given the ratio and 2 single unit amounts, then label that equality 2A plus R for 2 amounts plus ratio. So determining whether we have the ratio or 2 amounts plus a ratio requires a very careful reading of the question. For example, if 0.24 grams of sodium hydroxide are dissolved to make 250 milliliters of solution, find the sodium hydroxide concentration. So we know that we can write the equality 0.24 grams of sodium hydroxide equals 250 milliliters of solution. But which label do we want to attach here? Well, the data that we've been given are 2 amounts that each measure the same thing, that's solution. That is, we know the mass of sodium hydroxide in solution, and we know the volume of solution. And thus, we need to label it with 2A plus R. So we've got down here our data, and over here we've got a 2A plus R in parentheses next to our equality. Let's look at another example. The conversion between fluid ounces, an English unit, and milliliters, an SI unit, is 12 fluid ounces is equal to 355 milliliters. What is the number of milliliters per fluid ounce? Well, we know we can write the equality 12 fluid ounces is equal to 355 milliliters. But which label do we attach? So we've only been given a ratio between the 2 units. We've not actually been given any single unit amounts. And thus we need to label it with an R for ratio. Let's look at another example. A soda can is labeled 12 fluid ounces is equal to 355 milliliters. And what is the number of milliliters per fluid ounce? Well, we know that we can write the equality 12 fluid ounces is equal to 355 milliliters. But which label do we attach now? Well, in this case, we know the volume of the can in fluid ounces, 12 fluid ounces. But we also know that volume of the can in milliliters, 355 milliliters. And thus, we have 2 amounts and a ratio. So we need to write that 12 fluid ounces equals 355 milliliters, and then in parentheses, 2A plus B for 2 amounts plus the ratio. So determining whether we have just the ratio or 2 single unit amounts plus the ratio will require some practice here. So be sure to do the practice problems in this lesson, both in practice A and in practice B, and those practice problems at the end of the chapter. Now, let's add one more label that we use in our data section. Let's add single unit amounts, or SUA. So single unit amount. Ratios will be labeled R, and then our 2 single unit amounts and the ratio will be labeled still the 2A plus R. And so most of the time that a measurement is written as a ratio with per or a slash, meaning per 1, it's going to represent a ratio but not 2 single unit amounts. So that was ratios versus 2 related amounts.